Okay, so like I was saying, in here in the gas chapter, as they are flying around, they are causing collisions, and again, causing that pressure that we associate with it. And common units of pressure are atmospheres. One atmosphere is equal to 760 millimeters of mercury, which is another very common unit of pressure. And that equals 760 torr, which is also a very common unit of pressure. Those being pretty much your top three there in terms of units: atmospheres, millimeters, mercury, and torr. With obviously 760 here being our conversion factor to go between those things, between atmospheres, millimeters, mercury, and torr. That also means, as we talked about, 1 millimeter of mercury is equal to 1 torr. It's basically a one-to-one relationship. So if he has to do that conversion, pretty much all you do is just change the unit. The number stays the same. It's going to be 1-to-1. Now, we talked about some gas laws. The first one we talked about there was our friend Boyle. He dealt with the pressure volume relationship, holding temperature constant, and gave us P1 V1 equals P2 V2 at constant temperature. And here the pressure could be any unit you want. The volume could be any unit you want. Again, you just need to make sure that they are the same units on each side of the equal sign so everything properly cancels out. The relationship that we see here with Boyle's law is as the pressure goes up, the volume goes down. So sort of an opposite relationship there. And vice versa, pressure goes down, volume goes up. Again, in a much smaller volume, we're going to have gas molecules having a lot more collisions as there's not a lot of room for them to fly around. And then we will start to see the pressure increase. Vice versa, there in a more larger volume, that'll give the gas molecules a lot more room to fly around in. That will actually cause the number of collisions to come down, and we will see the pressure decrease because of that. We had our friend Charles here, law, which is V1 T1 equals V2 T2. This was at constant pressure. And in this case, volume can be any unit you want, but remember that if you are dealing with gases, that is going to be Kelvin for any type of temperature value. Once again, as I might have mentioned, even if the problem gives it to you in Celsius and wants the answer in Celsius, it does need to go to Kelvin and then into gas law, and then you have to convert it back at the end. The relationship that we see here is actually the volume will go up as the temperature goes up. So as the temperature increases, gas molecules are flying faster. In a situation that would normally cause greater pressure because there's going to be more collisions happening. But what allows it to keep a constant pressure is the volume will adjust. So the volume will get larger, give everybody a little bit more room to fly around in, even though they're moving faster. What that will essentially do is keep the number of collisions pretty much the same as where it was at. And that's how the pressure stays constant. Same idea here, volume down, temperature down. If we lower the temperature, gas molecules are going to be flying around slower. And again, that would normally cause a decrease in pressure because there's going to be less collisions. So what ends up happening is the volume squishes everybody to a very small area. And even though they're moving slower, we're still going to be able to maintain the same number of collisions. And that's, again, what keeps pressure constant. So in Charles' law, what allows basically that pressure to remain constant is that the volume basically will adjust depending on what the temperature is doing. That's different than we see with Guy-Lussac's law. And in that, we have P1 T1 equals P2 T2. And this is actually at constant volume. In this situation, obviously, once again here, temperature Kelvin. In this situation, the volume is fixed, which means it cannot adjust. So what we actually do see is what we expect to happen. As the temperature goes up, we will see an increase in pressure because the volume is not going to adjust in this case, and you're going to have a lot more collisions because everybody's flying around faster, and vice versa. Temperature down, pressure down, slower moving molecules, less collisions, lower pressure. Again, we're not going to get any type of volume adjusting in this situation like we would have in Charles' law. We also, I think, just touched upon our friend Avogadro because we can't leave him out. He also has a law, and that's V1 N1 equals V2 N2. This is actually under two conditions. This is constant temperature and pressure. And N here is the number of moles. And we do volume doesn't matter what it is. The relationship here is kind of as the volume increases, so is the moles. They're almost proportional to each other. As the moles increase, so is the volume of the gases. Putting all these guys together gave us the ideal gas law that we talked about there. And that's our PV equals nRT. And a reminder that this one is different than all the other ones. There's just kind of a one and done thing on this formula here. We don't have two pressures. We don't have two volumes, basically just one of everything. This also is the most restricted in terms of units. When you put numbers into this equation, pressure has to be atmospheres, volume has to be liters, N, which is moles, should be moles, and T does need to be in Kelvin. And it's all because R is the gas constant, 0.08206 liters atmosphere Kelvin mole. And again, sometimes books and people will use a rounded version of that number there, 0.0821. I don't really care whichever one you use if you like. Remember that with R, it is very commonly not even mentioned in problems. So again, that's just a number, as we talked about, that they assume that you have available to you to use, but probably very rarely ever will be mentioned at all in a problem or anything like that. So, if you're kind of pulling information out for the problem, like we talked about, it's a good idea to do. And you see, like, I have almost everything I need for the ideal gas law. That's probably the thing you're missing is the R value. And again, very commonly not mentioned in problems that are given to you just straight out and stuff like that. So something they sort of expect you to know. We also talked about the idea of STP, that is standard temperature and pressure. And when we have something at STP, it does have values. The temperature is 273 Kelvin, pressure is 1 atmosphere. And there's a nice relationship that if you are at STP, 1 mole of any gas will equal 22.414 liters. And you could kind of use that conversion without necessarily having to use the ideal gas law, but it has to be at STP conditions. So if it is not a temperature of 273 and a pressure of 1 atmosphere, you should never use that. You should always use the ideal gas law. As I mentioned last time, you can always use the ideal gas law. You can use it in STP conditions. You can use it in non-STP conditions. You can use it in any condition you want. So the ideal gas law, if you're unsure of, you could always go into there and just not even worry about that conversion and just put the numbers in there and everything will come out the same. We finished up with obviously maybe one of the most important gas laws, which is the combined gas law. And that is really our P1, V1, T1 equals P2, V2, T2. And once again here, Kelvin for our temperature. This one again is really important, or even the version that has the moles in it, if you want to remember, again, as we talked about, sort of that version. And again, from this gas law, you pretty much could get all those other gas laws that we just talked about. So again, a reminder that, if you invest your time on this one, it's a good one to remember. And just remember that if it has anything in the problem that's held constant, or anything that they don't even mention a value for, like, again, if we come across a problem where there's no moles or temperature mentioned, all you got to do is scratch it out, and then you would have Boyle's law, and again, the right gas law that you probably need to use. So I would roll with the combined gas law memorization there, and definitely the ideal gas law. And between those two, pretty much you should be able to solve any gas law problem that you would come across by just knowing basically those two. And more importantly, knowing how to obviously adjust the combined gas law to just scratch out what you don't need, and you'll be left with what you do need. Any questions on any of those things there? All right, so I don't think we did the example, so why don't we do that one now? Let's go find that example wherever I put it. There it is somewhere, maybe. Maybe there's a lecture here today. Let's see here. No, that's way too far back. All right, so it is coming up. Anticipation. There it is. Let's give this one a go here. Consider oxygen gas. We got it at 27 degrees. It has a volume of 9.55 liters, got a pressure of 2.97 atmospheres. We changed pressure to 8.25 atmospheres, and we heat it up to 125 degrees Celsius. What will be the new volume of this gas? So give it a go, see what you come up with. Okay, so let's take a look, see how we're doing. Remember that when you're dealing with gas laws, it's really important to just kind of pull out the information, kind of label what it is a pressure or volume, temperature. And a lot of times, if you do that, and you're not really sure what gas law you should use, you could kind of see the gas law like looking at you. So, for example, here we have a temperature that's 27 degrees Celsius. That goes with a volume that's 9.55 liters and a pressure that is 2.97 atmospheres. We have another pressure that is 8.25 atmospheres and a temperature of 125 degrees Celsius, and we're looking for a volume. So in this case, you could hopefully kind of see the combined gas law looking at you. We talked about this last time, just in order of how it's written in the problem. It's usually how we number these things, ones and twos. And again, that would give us P1 V1 over T1 is equal to P2 V2 over T2. In this particular case, we are looking for V2. Remember that the quick way to rearrange the equation is if you go across the equal sign, it ends up in the opposite location. So that means we'd have to move the T2 to the top and the P2 to the bottom, and that will rearrange that correctly. That's basically multiplying by T2 and dividing by P2 in this case. That will give us, when we rearrange it, P1 V1, and we're going to bring T2 to the top, divided by T1, and we're going to bring P2 to the bottom there, and that will equal our V2. Remember, whatever you're solving for does need to be on top, not on the bottom. If I solve for something that's on the bottom, that means I'm not really getting what I'm looking for. I'm getting 1 over what I'm looking for, so you'll have the inverse of what you're actually looking for. So whatever you're trying to solve for should be up on top by itself. And in this case, we do need to do a little conversion here. Atmospheres are good. Like normal, as I mentioned last time, it's almost a no-brainer in gas law problems. Pretty much just add that 273, get everybody into Kelvin. And if we do that, they're 125 and 273. Going to give us a 398 Kelvin there. And on the other side there, it looks like 300. I'll go this way with it. Now that we have everybody in the right units, we could put it in here. And again, we want to be careful to put everybody in the right spot. So P1's up on top, 2.97 atmospheres. V1, 9.55 liters. And our T2 is up on top, which is 398 Kelvin. That's going to be divided by our T1, which is 300 Kelvin. And on the bottom there, P2 of 8.25 atmospheres. And that's all going to equal our V2. Our atmospheres on top and bottom will cancel. Our Kelvin on top and bottom will cancel. That tells us that we're going to be left with liters as the units that we have here. So we're just going to multiply what we got on the top there, 2.97 times 9.55 times 398. Remember to hit equals at this point. Divide by the first number on the bottom, which is 300, hit equals. Divide by the second number on the bottom, which is 8.25, hit equals. And you're going to get yourself a 4.56 liters in this case. Any question on that calculation there? So again, if rearranging the equation is problematic for you, take some time to make sure you know how to, again, properly rearrange it. But really, if you want to keep it simple, just opposite location if you move it to the other side. Yeah, so it just ends up in the opposite location. Any questions on that there? All right, there's all our answers. All right, the next thing we're going to talk about is Dalton's law of partial pressures. And sounds like a very complicated thing. But again, we just want to kind of keep it simple here, which is the idea is if we had a container, for example, and within that container, the only gas molecule that we had flying around was gas molecule A. That would mean in this particular case, the total pressure of that container would be all result basically of just gas molecule A, basically, that's flying around, as that's the only one in the box causing collisions, right? Now, if we pop into a box here, or a container that could hold gases, and we put gas molecule A in there, we drop in there B, we drop in there C, we now have all these gas molecules, different gas molecules flying around in that container. And the total pressure in this case will actually equal the partial pressure of A, the partial pressure of B, plus the partial pressure of C. These are what are referred to as partial pressures because they are each contributing to the overall pressure of that mixture of gases. So the idea of partial pressures is pretty much this. If you have a mixture of gases, which is very common, and they're in the same container, the total pressure of that container will be a result of all the individual gases, basically individual pressures, and that is what is referred to as partial pressures. So how do we get the partial pressure? I would say probably the most common way that you could get the partial pressure of each gas is to use our friend the ideal gas law and solve for P. And you would solve for P, which would be nRT divided by V, and you could do it for each gas that's in that mixture. One of the nice things about this sort of mixture of gases is because they are all in the same container, you will have the same volume for everybody that's in there. And because probably that container is in the same room, obviously, it will have the same temperature for everybody. That means when you look at the ideal gas law that you're going to use, V will be the same for everybody, T will be the same for everybody, R is a constant, which means it will be the same for everybody. So really the only difference that you really will have to calculate for each of the gases that are present is N, which is the moles of gas. So the N will typically be different. And once you calculate the moles of the gases, you then can put them again individually into the ideal gas law. You would get 3 different pressures in my example here, one for A, B, and C. Again, those would be the partial pressures of A, B, and C. And to get the total pressure, you simply just add them together, basically, and that will give you the total pressure of that mixture. Any questions on that there? Now, when we look at these partial pressures, they should add up. And one of the reasons why we can sort of do 3 different calculations for these gases, even though they're in the same container, is because we are assuming ideal conditions. And one of the things that makes something an ideal gas is, as we might have touched upon a little bit last time, the idea that in an ideal situation of temperatures and pressures, you could have multiple gases in the same container and they pretty much will not interact with each other. So in an ideal situation, it's almost like they're in there by themselves. And that's how come we could treat these type of calculations like this, that they're in there by themselves, even though they're with other things, because there is no interaction. So having A, B, and C gas molecules flying around in the same container, they're not going to, in an ideal situation, interact with one another. So we could do 3 separate calculations like they were in there by themselves and then put it together to figure out the total pressure. So that is one of the main reasons why we're able to do calculations like this, is because we're under ideal situations, so we don't have to worry about any type of interactions between the different gas molecules. Any questions on that there? So here's pretty much what I just wrote there. Again, we're just going to basically do the ideal gas law for each gas separately and then add up each of the partial pressures when we're all done. Obviously, here we're going to use the ideal gas law, which means, again, we need to be careful about units. So as we talked about a second ago, obviously moles should be moles, temperature needs to be Kelvin, and volume needs to be liters. So everybody needs to be, again, in that right unit. And R obviously is still our gas constant, which you always have available to you. All right, so why don't you try one here? We got 5 grams of helium is added to 5 grams of neon. We put it in a 2.5 liter container at 27 degrees Celsius. We're looking for the partial pressures of each gas and also the total pressure. I'm going to give you some numbers that might be helpful here. Helium is 4.003 and neon is 2018. We're looking for 3 things. We're looking for the partial pressure of helium, partial pressure of neon, and we're looking for the total pressure of both of them together. Let's see what you come up with here. Again, basically an ideal gas law for each. Yes. Grams of helium And we also have 5 grams of neon. We're going to put it into a container that is 2.5 liters. We have a temperature that is 27 degrees Celsius. And we're looking for partial pressures, which basically means we're looking for P. Obviously, here we have one of all information, so that should direct you really to PV equals nRT. Remember that although never given to you in problems, you always have R, which is a constant value. So here we're going to send volume to the other side really and solve for the pressure here of each of these gases individually. We do have the temperature, we do have R, we do have V. The only thing that we do not have in addition to the pressure that we're looking for is moles. But we do have the grams of each of these guys, and we can convert the grams into moles by using the molar mass from the periodic table, hence these guys. Yeah, so we could use those, convert them into moles, and then we'll have what we need almost. So I'm going to do that first. So I'm going to look for my moles of helium. I'm going to take the grams of helium, which is 5. I'm going to use the molar mass from the periodic table as a conversion factor to convert from grams to moles of helium. And if I do, it's going to give me a 1.25 moles, I'll call it, of helium. I'm going to do the identical calculation here for neon, except obviously here I will use neon's molar mass, which again from the periodic table is 2018 grams per mole of neon. Going to get us 0.248 moles of neon. Any question on that calculation there? That I would say is also very, very common in gas law problems. You're given things in grams, you need to convert them to moles using the molar mass. Now that I have that, I have everything I need for the ideal gas law, except like normal, I gotta add my 273 here to my temperature to get it into Kelvin, and that looks like a 300 Kelvin. Our volumes in liters, so that's good to go. Remember as well, a very common conversion is milliliters to liters or liters to milliliters as well, that you need to kind of do. So I'm going to start with the helium here. The partial pressure of helium will equal nRT divided by V. Putting in the moles of helium, 1.25 moles. Putting in my gas constant, 0.08206 liters atmosphere Kelvin mole, and my temperature of 300 Kelvin, all divided by my volume of 2.5 liters. The moles will cancel, the liters will cancel, not the, sorry, the liters will cancel, the Kelvin will cancel, cross out the right one there. And we will be left with atmospheres, which is good since we're looking for a pressure in this. Again, make sure you hit equals after the top line there. We'll call it 12.3 is known as the partial pressure of helium in this particular case. Question on that there. We're pretty much just going to repeat that. Other gases in the container, and because they're in the same container, again, they have the same volume, the same temperature. It's pretty much the identical calculation, except I just need to use the moles for my neon instead of obviously helium. So if we do our pressure of neon, it will still be nRT divided by V. The real difference here is we're going to use the moles of neon, obviously, instead of helium. Everything else is going to be identical, exact same values, because frankly, they're in the same container. They're under the same conditions. The only difference is how many moles we have. Same cancellation here. If I wrote moles, moles cancel, Kelvin cancels, liters cancel, leaving us atmospheres here. And we will end up with 0.248 times 0.08206 times 300 divided by 2.5. It's going to be a 2. The last thing that I'm looking for is the total pressure. What should I do with those two numbers? Yeah, we're just going to simply add them, right? So partial pressure of helium plus the partial pressure of neon would get us a 12.3 atmospheres plus a 2.44 atmospheres. And you throw your calculator in the sink, you get it out of the sink. 12.3 plus 2.44, 14.7 atmospheres would be our total pressure. Any questions on the calculation? It's basically just the ideal gas law. Again, volume, temperature, the same for everybody in the mixture. Really, the only difference is going to be the moles, and then you add them together at the end. Which one's contributing more pressure? Helium or neon? Yeah. The reason for that is, let me know. It has to actually do with these numbers. Helium is much, much lighter. Yeah. So since it's lighter, it's going to actually be flying around at a very high velocity, much faster than neon. And because it's flying around a lot faster, it can cause more collisions and more pressure because it's a lighter gas molecule. It's going to cause a lot more collisions. Any questions on that there? Cup. Now, another very common sort of partial pressure situation is maybe this one that looks familiar to you. Maybe. Terrible lab. Was something like this when we collect gas in the laboratory. A lot of times, based on the way we collect it, we cause sort of a situation to occur. So this is a little potassium chlorate action here, which I think you might have done. And if you heat the heck out of that thing, it will decompose into a little potassium chloride and a little oxygen gas in this case, right? And in this case here, we do a little balancing, I suppose, would be good. 2, 2, 3, maybe. And in this case, we're going to produce oxygen gas. So as you heat this, and hopefully you put a bunch of that in there, otherwise you're probably there all day. If you didn't put a lot of that catalyst in there. The oxygen gas will come through this tube into this container where you typically have water in it. And as the gas goes into the container, the water goes out of the container, sort of displaces it. And you end up with this empty spot usually in your container. It's really not empty. It actually has the oxygen gas that you generated in this particular example. But as a consequence of how this water or this gas was collected, water is involved. And when you do a little reaction with water, it doesn't take a lot for it to heat up. And you will also collect some water vapor. So what you end up with in this case is actually a mixture of two gases in your experiment. And frankly, you're not interested at all in the water. You're really just interested in the oxygen part. So you get the total pressure in this case would equal the partial pressure of the gas you're interested in times the plus the partial pressure of water. And that's what is sometimes referred to as the vapor pressure of water. And that usually is a value you can look up on a table. That's usually a value you can find on a table. And we can use this, and in the laboratory, that's your barometer reading for today. That is usually what that value is. And you can use this equation and actually rearrange it, and the partial pressure would equal the total pressure minus the vapor pressure of water. It's kind of like a correction value that you typically do in experiments like this to subtract off the contribution of water because you're frankly not interested in it. You're really interested in my example here of the oxygen gas that you collected. You're not really interested in what water's doing and stuff like that. So the nice thing about this type of partial pressure one is it's just a subtraction type of problem. So you take the total pressure, which is again usually the barometer reading, minus the vapor pressure of water at the particular temperature that you may have to look up in a table. And that will get you the pressure of the gas. Sometimes in labs and stuff, they refer to this as the pressure of the dry gas. And that is because you subtracted off water's contribution basically to the pressure in this case. So anytime you collect a gas and water is involved, you usually have to do this type of correction sort of calculation, which is really, again, a sort of partial pressure situation that's happening. All right. So let's take a look at one here. A sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of the gas in atmospheres? So this is basically the exact same situation we were just talking about. The key words that you know that you typically have to do this in a problem is it will say something like this. Hey, it's saturated with water vapor. Or they'll say you collected it over water. They'll mention something to do with water, and that should automatically to you kind of pop this equation into play. And in this particular case, they were nice enough to give us the vapor pressure of water at 30 degrees. And in this case, it is that number there, 31.824 torr. The total pressure or the barometer there is 753 torr. So we have this guy, we have this guy. So once again here, we can rearrange for the oxygen gas by subtracting this to the other side. And that will give us that the total pressure is minus the vapor pressure of water. And if we put our numbers in, we will have 753, which is our total pressure, minus our table value. And again, if it was not given to you in the problem, which commonly is probably not going to be, you need to look it up in a table that should be in that gas chapter. And it's usually based on temperature is sort of what you look it up as. And we'll take 753 minus 31.824. Going to yield us something like 721 torr. We are looking for it in atmospheres, and that is where that 760 number comes into play. 760 torr is 1 atmosphere, so those guys will cancel. And that will get you, we'll call it 0.949 atmospheres as our basically pressure of the oxygen gas in this case. And that's the dry oxygen gas getting rid of our sort of water contribution. You could also do this type of partial pressure problem if you know basically the total pressure of the mixture and you know one of the other partial pressures, or if you know obviously both partial pressures, you could add them together. So you kind of use the adding and subtraction fairly easy if you know kind of 2 of the 3 things or 2 of the 3 things, depending on how many gases you have going on. Any questions on that there? So this is the kinetic molecular theory of gases, and these are some important parts that you should know. Gases consist of tiny particles or atoms or molecules. These particles are small compared to the distance between them. So the volume of the individual gas molecule is not important. So as I mentioned, I think the other day, that's why when you read a lot of problems, they talk more about like the volume of the container the gas is in rather than the volume of the gas molecules themselves. That is one of the things that makes something an ideal gas. We ignore the actual volume of the gas molecules themselves. Is more important the volume of the container they're in, that they're flying around in, rather than the actual individual gas molecules. Because their volume compared to the volume of the container they're flying in is much, much smaller and almost negligible in that calculation. The particles are in constant motion and colliding with the walls of the container. These collisions, again, is what causes the pressure we exert or we think of with gases. The other gas is this one right here. And that is, as I mentioned before, that we assume that there's no attractive forces or repulsion type forces in an ideal situation. So again, that is why when we do our partial pressure calculation like we just did, we can basically do the ideal gas law for every gas individually, even though they're all in the same container. They're not going to, in an ideal situation, have any interactions with each other. And we can almost assume like they're in there by themselves, which allows us to do that type of calculation. If you're dealing with a real gas, which we do not deal with in here, real gases, you do have to actually take both of those things into account. The size of the gas molecule itself and actually its interaction with other gas molecules. It creates the ideal gas law that looks really scary looking, and it's known as the van der Waals equation. But that only occurs at really high pressures and really low temperatures as well. But we don't deal with that. So everything in here will be an ideal situation. The average kinetic energy of the gas molecules is related to the temperature. Temperature increases, we expect the gas molecules to fly around faster. If it decreases, we expect them to kind of slow down. Any questions on that there? Just to finish up on some of the parts and relationships that we talked about. Again, temperature is a measure of the motion of gases. At higher temperatures, we have, again, those gas molecules moving faster, hitting the walls of the container. Again, could be increasing the pressure. Lower temperatures going to be moving slower, the gas molecules. We would expect less collisions. Pressure and temperature, the pressure in a rigid container, so that's going to be a container like in Guy Lusik's situation, where the volume will not adjust. And in that situation, the pressure will start to increase as you increase the temperature, as we talked about. Again, just because they're going to be flying around faster, volume's not going to move, a lot more collisions, a lot more pressure. Opposite is true, obviously, if you lower the temperature in that situation. Volume and temperature, remember, again, in Charles' situation, it is the volume that adjusts to allow the pressure to remain constant, and it will adjust the same way as the temperature. Temperature increases, the volume increases, gives everybody more room to fly around in, and temperature decreases, the volume will squish them down and put them closer together. Any questions on any of that there? That is chapter 8, the gases. No, 7. Solutions are homogeneous mixtures, which means they usually look the same throughout, means things dissolve in each other. And solutions are the guys that have the AQ symbol next to them, the aqueous symbol. So AQ means aqueous, means it's a water environment. There is a difference between aqueous and L. L is liquid. How you make an aqueous guy? You take something like water, which is a pure liquid, and you mix it with something like sodium chloride, which is a solid. That sodium chloride will dissolve in the water, and it will make a sodium chloride solution that is aqueous. And again, so aqueous implies it's a solution and that it is a mixture of two things that dissolve in each other. It's a homogeneous mixture, which means everybody's going to mix nice and everything's going to look the same throughout, right? Again, a pure liquid is just by itself. So again, there is a difference between L and AQ. So let's talk a little bit about solutions and the different parts of it. Many reactions occur in an aqueous solution and an aqueous environment. And a solution itself, as I mentioned, is a homogeneous mixture, and it's actually made up of two parts. There is the solute, which is the smaller part of the solution, and there is the solvent, which is the larger part of the solution. Typically, your solute will dissolve in your solvent. So the example I just did, where I took my water and I put some sodium chloride in it, and it dissolved and it made a sodium chloride solution. Water, in this case, is my solvent. My sodium chloride is my solute. It's the stuff that will dissolve in it, basically. Together, they will make a sodium chloride solution. How do you know what the solute is when you have a solution? It's pretty simple. It is the name of the solution. So if I have a sodium chloride solution, sodium chloride is my solute, yeah? If I got a potassium chloride solution, potassium chloride is my solute. If I have a hydrochloric acid, hydrochloric acid is my solute. So whatever the name of the solution is the solute. I will say that a lot of times water is a solvent, but it is not a good solvent for everything. For ionic and things that are polar, water works really well. But for things that are non-polar, it does not work well at all. So 9 times out of 10, probably water is going to be your solvent, but it will not always be the solvent. So it does not always has to be the solvent. So here's copper 2 sulfate, the solid before you begin. That is our solute. Our water against our solvent, much larger. Give it a mixy, maybe a shaky, right? And those guys break apart. Those ions start floating around, right? By the way, this in solution is where we find ions, yeah? So when we have a sodium chloride solution, it's a strong electrolyte. It's basically all sodium ions floating around. It's all chloride ions floating around in that solution. So if you ever wondered where are ions, ions are in solution. They're floating around in the swimming pool, basically, yeah? Floating around in that part of it. Now, as I mentioned before, water is a really good solvent for a lot of things. There is this idea when we talk about things dissolving in other things known as like dissolves like. And what that means is if you take something that's ionic, it will be pretty soluble and mix really well with something that's polar. If you take something that is polar and you put it with something that is polar, they're going to mix okay. If you put something that is nonpolar with something that is nonpolar, it will also mix. So all these guys would be soluble in each other. They all will mix in each other basically, and everything will. It is only typically when you cross over from polar to nonpolar that is very problematic. They're typically going to be insoluble in each other. They will not mix like oil and water. You can mix that all day. The oil and the water will eventually separate out from each other. The reason for that is, and when we talk about things being polar and nonpolar, we're talking about what we talked about with bonding, molecular polarity. The molecule is either polar or nonpolar. If you remember what that means is if something is polar molecule, it means that they are not sharing the electrons equally overall the whole molecule. And what that really means is when you have a polar molecule, there is a positive side to that polar molecule and a negative side to that polar molecule. Like water. Water is a polar molecule. The hydrogen side is more positive. The oxygen side is more negative in water. And that allows it to interact really well with other polar molecules because pretty much how all molecules interact with each other is a basic interaction of opposites attract. So the positive side of one of those polar molecules will be attracted to the negative side of another, and they will mix really, really well together. That is also why something like water, which is a polar molecule, is really good for ionic compounds because ionic compounds have charges because they're really made up of ions. So when you drop something like sodium chloride into water, you get a sodium ion, you get a chloride ion. And what happens is the water molecule will surround the positive ion with its oxygen, which is negative, and help that sodium chloride dissolve in solution. Same thing will happen with the chloride. It's negatively charged. The hydrogen side of water, which is positive, will start to surround the chloride ions, right? And when you look at that and you take some salt or something in water, we help this process along by stirring, right? When you stir it, you throw a bunch of water molecules all over that ionic solid. The ionic solid to start with is just all clumped together, basically, which is why you can see it, those positive and negative ions together. But when you stir it, you throw water molecules on there. You also add energy. That allows those water molecules, because there's so many of them, to pop those ions off, basically, and start surrounding those ions. There's so much water molecules when you dissolve something like salt, right? It looks like it disappears, right? And it does because you can't see it anymore because there's just so many water molecules surrounding those ions that it is not visible to you anymore. But it's still there, as you might see in this experiment this week, maybe, or maybe you've done before. You heat up a solution of sodium chloride, right? And you can't see any solid. When you heat it up, when we heat up something that has water, that's going to evaporate off all these water molecules, right? And you'll get rid of all those water molecules, and there'll be nothing in the way of those two ions sticking back together, and you will see the solid come back, right? And that's how we know it's actually a physical change when you do a solution, because nothing is lost. What we start with and what you end with is still there. You just can't see it. It looks different when it's dissolved in a solution type form. Any questions on that? By the way, nonpolar works really well because they both use what is known as dispersion forces, which are actually pretty weak forces. They basically both don't have charges, so they interact really well. That's why when you take something that's nonpolar and polar and put it together, they have a real problem, because nonpolar things, which are kind of neutral, wants to use these dispersion forces, which are these really weak, bad interactions. Something like water wants to use these polar forces, and those are not two of the same type of interactions. So they're not going to be able to interact well with one another for a long period of time. That's why they cannot maintain that interaction like oil and vinegar salad dressing, right? You can shake it up, right? It mixes, but if you leave the bottle on the table, it eventually does what? Separates out, right? Because it cannot maintain that sort of mixture and those interactions over a long period of time. They can do it for a short period of time, but there's just no way to allow it to stay there. Any questions on that there? And here's a picture of what I was talking about. This is basically what something like sodium chloride looks like in a solid form, just all the ions stuck together in a very organized fashion. And again, when you throw your water on there and start stirring it, it's able to pluck off those ions. Eventually it will dissolve and not look like it's there. Here's another picture of that and a third one in case you didn't like the first two. Same idea here. So let's talk a little bit about these examples of solubility in water. As I mentioned before, ionic compounds are good to go with water because they're able to do those opposite attraction. The water will just surround the positive ions. They'll surround the negative ions. They will help everything mix. They'll work themselves into the water mixture. But we also have non-ionic compounds like sugar and ethanol, which are also very soluble in water. And the reason for that is if you look at something like ethanol, it looks something like this. And if we look at something like water, it looks something like this. And water, as I mentioned before, is more negative on the oxygen, more positive on the hydrogen. How water interacts with itself and how molecules interact with one another is through what is known as an intermolecular force. And an intermolecular force that water uses with other water molecules is basically the positive side of one water molecule is attracted to the negative side of another. This is what is known as hydrogen bonding. All right, this way. Hydrogen bonding. Hydrogen bonding is a type of interaction which is known as a dipole-dipole interaction. You might also remember the word dipole. We saw it with polar molecules. They have dipole moments, yeah? So that's why it's called dipole-dipole interaction. But two water molecules, how they interact with one another is through hydrogen bonding. Hydrogen bonding has to occur between you. The only way you could do hydrogen bonding is you need a bond between hydrogen and an electronegative element like nitrogen, oxygen, or fluorine. So that hydrogen has to be directly attached to an oxygen, nitrogen, or fluorine, which it is in water. Clearly that hydrogen here is attached directly to the oxygen, so it's able to hydrogen bond. This hydrogen is directly attached to that oxygen, it's able to hydrogen bond. So when we look at ethanol, it actually has that exact same bond that you see in water. It has that OH group. So it has a negative and a positive. That's a polar bond, which when it hooks up with water, works really well because it could also hydrogen bond with water. So it's able to hydrogen bond with water the same way that water could hydrogen bond with somebody else. And that makes something like ethanol really, really soluble in water because it has the same type of interaction. Now, just to verify all these hydrogens here, can they hydrogen bond? The answer is no, because they are not directly attached to a nitrogen, oxygen, or fluorine, right? They are actually directly attached to a carbon. And that's actually not going to create a polar bond. It's a non-polar bond. So even though there's hydrogen present, it cannot always hydrogen bond. It has to be the hydrogen that is directly attached to a nitrogen, oxygen, or fluorine, like we see at the end there. Ethanol has two parts. It has a non-polar part, and it has a polar part up here in front. Sugar as well is also very soluble in water. Sugar is a little larger of a molecule, but it is littered with OH groups everywhere. So it has a lot of OH groups everywhere. And everywhere there's an OH group, it allows it to interact well with water. and it makes something like sugar quite soluble because of those OH groups. Okay, let's continue on then. We are talking again here about really solubility in water, and if something is soluble, again, it pretty much means that it mixes. It all comes together in a nice solution. If it's a solid, it will dissolve. Obviously, if it's two liquids and they're soluble, they'll mix, and it'll all just look like one liquid, basically, if you put it together. As I mentioned before, something like ethanol or sugar are going to be really soluble because they do contain on them groups that allow them to interact well with water through this process of hydrogen bonding. And again, really, it's just sort of opposite attraction there between the hydrogen and, say, the oxygen there. So here's, again, a picture of that. This is actually methanol, which is like ethanol with one less carbon. But again, here you can see it also has the OH group. And again, going to be able to do the hydrogen bonding there with those water molecules. And it's going to be able to interact really well. Now, ethanol and methanol aren't super large molecules, which also helps to sort of interact. Remember that if you're going to dissolve something in water before you do that, you pretty much have to break apart all these water type molecules, right? And sort of replace them with whatever you're trying to dissolve in there. And again, if something's really, really big, it creates sort of a problem for that to happen. But if it's small and has a way to interact well with water, it's going to make it very, very soluble. Here's our ethanol example again, our hydrogen bonding there happening. Now, what about oil and water? Do they mix? They really do not. And oil is insoluble. The major sort of component of oil is basically a bunch of carbon to carbon bonds and carbons attached to hydrogens, basically. So it's carbons and hydrogens all the way across. And those are all nonpolar bonds. And as I mentioned before, what happens with oil, because it essentially is nonpolar, because all it's got going for it are these bonds here, it's not going to have any way to interact well, and it just kind of keeps going very long on each side, because it's going to want to use, again, those dispersion forces, which are those relatively weak intermolecular forces. And water, again, is going to want to use basically hydrogen bonding to interact. And those are very, very different types of forces. And again, they're not going to be able to maintain that. What is a dispersion force and why is it so weak? It's so weak because basically, if you have two nonpolar molecules, they're basically neutral. So they can't really interact with each other until somebody gets some charges. So they have to rely upon something happening to them to give them a charge. So one thing that could happen to a nonpolar molecule is all their electrons, for example, may end up as they're moving around to be on the right-hand side of the molecule versus the left-hand side of the molecule as they're flying around. You get this big amount of electrons all heading to one side. The result of that is because of that unequal sort of electron flow, this nonpolar molecule, which normally doesn't have a charge, will now temporarily gain a charge. And if it's still sitting next to another nonpolar molecule, all the electrons in this guy's going to go, that's negative. I don't like that. I'm going to go this way. And all those guys' electrons are going to go to the opposite side of that molecule. So now on those two nonpolar molecules that didn't have charges, they will temporarily gain charges. And that's how that dispersion force is able to interact. It's temporarily because when those electrons come home from their vacation, they're not going to no longer have that charge and it's going to fall apart and make new interactions. And then those will fall apart and make new interactions and those will fall apart. So they're very, very temporary. And that is also why when you put something like water and something that's nonpolar together, something like a polar molecule can temporarily do that to a nonpolar molecule. So if that's a polar molecule, that's a nonpolar molecule, it could cause those electrons to kind of go the opposite way. And once again, you'll get this temporary sort of interaction between this polar and nonpolar molecule, that they can interact with each other. But once again, as soon as they kind of move away from each other, that nonpolar electrons are going to come back, and they're not going to be able to maintain that. Kind of like how we just talked about, at some point, everything will just separate out from each other. They're not able to maintain that interaction over the long period of time. So when we have something like oil, which is nonpolar, not going to be able to interact well with water, they are not going to be soluble in each other. The other problem with oil is it's super big usually. It's pretty long carbon chain, which means you're trying to park something into water, which is relatively small, and it doesn't fit really well. Again, like if you're trying to park a car in a garage, it's going to be fine, right? But if you try to put like a semi truck in the garage, you get some of it in there, but it's not going to fit just right, right? So it's kind of the same idea here. It's relatively big. It doesn't have good interaction with water, so it's going to make it very, very insoluble in this idea. Any questions on that there? That again brings up the idea of, as I mentioned earlier, of like dissolves like. Again, things that use the same type of intermolecular forces that they use with themselves will be able to use it with somebody else and interact well. Again, if you get two things that are using very different interactions, they will be insoluble in each other. Pretty much the main one of that is something that is polar and non-polar, trying to put them together, not going to happen. But if you have polar and polar, you're going to be good. You have ionic and polar, you'll be good. And if you have non-polar and non-polar, you'll be good. But again, if you cross over polar, non-polar, it's not going to work really well because they will not be able to interact with each other over a long period of time and keep that interaction going. Any questions on that there? So here's sugar, which is a relatively big molecule, but what the main advantage of it is, everywhere you can see it's littered with OH groups, and everywhere there's OH groups, it just increases the solubility of it in water. Here's pretty much what oil looks like, just a long old chain of carbons and hydrogens, non-polar all day on that one. And again, not going to be able to interact well with water. And that's typically what we do see, right? We see an oil layer, which is on top, and a sort of water layer on the bottom. And that's always happens, by the way, even in experiments you do, you mix some things together. Top layer is always the sort of organic non-polar layer. Bottom layer is the water layer. They separate out that way. Just like if you've seen an oil spill, right, in the ocean, the oil starts to float on top, right? You can see the oil floating on top. That's because it can't mix, right? And that's problematic. So let's talk a little bit about solubility. If one substance is going to dissolve in another, so if the solute is going to dissolve in the solvent, it's said to be soluble. So salt is soluble in water. When one substance does not dissolve in another, they are said to be insoluble in water, or insoluble in general. Oil is insoluble in water, again, because they will not mix. There is a limit to solubility. Even with things that are soluble in each other, there is a limit based on temperature, as to how much you could get to dissolve. You know, if you're sitting at a table, right, and you got those little sugar packets at a restaurant, right, you put it in your water, it'll dissolve, right? But if you go and get the Costco size thing of sugar and you got still your little cup of water, at some point, it's not going to dissolve all that sugar, right? It's just going to pile up. So there is a limit to how much you could get to dissolve at a given temperature, even if they are soluble in each other. Gases are always soluble in each other, and the idea of gases always being soluble in each other is they are flying around, so they're constantly mixing with each other, they're constantly passing each other as they're flying around, and they're always going to be soluble in one another. Some liquids will also be soluble, and again, that would be your polar and polar liquids together, or your non-polar and non-polar guys. And again, if you're mixing two liquids and they are soluble in each other, it will just look like this. If you're mixing two liquids and they're not soluble in each other, you will see different layers, right? Insoluble. Sometimes when people talk about liquids and liquids mixing, they talk about it being miscible, which means that they will mix and be soluble, or immiscible, which means that they will be insoluble and have different layers. But definitely put two liquids together and they don't mix, they're not soluble in each other, you'll see definitely different layers happening. But if they are, it would all just look like one solution, basically. How do we know if we put things together, whether or not we will get a solid or not? We could use solubility rules to help us determine if we throw these two ions together, Will we make a solid or will we not make a solid? So these are solubility rules from a solubility table. Group 1 is soluble in everything. There's no exceptions. So as soon as you see any member of group 1 in a formula, you know it's going to be soluble. And if something is soluble, those are the guys in equations that get the aqueous symbol next to them. So if something is soluble, it means it's a solution. Those are the guys who get the AQ or aqueous symbol next to it. If things are insoluble, those are the guys that get the solid symbol next to it, or the S symbol next to it. Anything that has ammonium in it, anything that has nitrate are going to be soluble in everything. There is no exceptions. Chlorides, bromides, and iodides are soluble in everything, but there are actually 3 exceptions. So all these guys are going to be aqueous. But if it's one of these 3 exceptions with chloride, bromide, or iodide, it does the opposite. It becomes insoluble. Sulfates are also soluble in everybody. It should be aqueous. But if you have one of these guys with the sulfate, it will be insoluble in this case. Now, there's also things that are typically insoluble. So if you see carbonates, you see phosphates, or you see hydroxides, these guys are typically going to make solids, except if they're hooked up with any of these guys, which are basically group 1 on the periodic table, then they will be soluble. So how does this work? If you think about a double displacement reaction or a precipitation reaction, you take a little silver nitrate, and I add a little sodium chloride to that. A little double displacement reaction, positive, negative, going to make sodium nitrate and silver chloride. We could use these solubility rules here to determine what everything is going to be. You may not be able to find both things in the table, but you should at least find one. So in this case, I see nitrate on the table. Nitrate is soluble and there is no exceptions, which means I know as soon as I see that nitrate, this guy is going to be a solution. It's going to be aqueous. Sodium is group 1 on the periodic table. Boom, that's right there. As soon as I see that, I don't have to look any further. There are no exceptions. I know that is always going to be soluble in this case. Same thing over here. I look at sodium. I don't need to go any further, but if you did, you would also see nitrate, which both tells you is going to be aqueous. I see chloride here, which is right here. It is soluble in everything except what 3 things? Silver, lead, or mercury. In this case, the chloride is actually attached to silver, which is an exception. So instead of being soluble, it's going to do the opposite. It's going to be insoluble, and you will make a white solid. You maybe did that during some chemical reactions. You get like a white solid that is formed. So this is how you can use solubility rules to determine if you put 2 ions together, would you expect a precipitate to happen or not? A lot of times used in double displacement reactions or precipitation reactions to help you decide what you would get. Question on those there. So why don't you try one here? Let's say I did this reaction. Trying to remember what I'm going to do. Yeah, let's do this one. Plus this goes to this plus this. All right, use the solubility rules here to determine is it aqueous, these guys, are solids. Again, aqueous for things that are soluble, solids for things that are insoluble. See, so again, like I said, you may not be able to find both things on the table, but you should, again, at least be able to find one of the things. So here's potassium, which is group 1 on the periodic table. That is right here. That is soluble pretty much in everything. So because it's soluble in everything, there's no exceptions. That's as far as you need to look. That is going to be aqueous. That will be a solution because it has potassium in it. Here, lead you may not find on the table, but nitrate is what we see here, and nitrate's on the table, and it also is soluble in everything. There's no exceptions. So because that has nitrate in it, I know that's also going to be a solution, which is why if you ever look at the solutions in lab, a lot of them are something nitrates, and then they're in the solution bottles because they're pretty much soluble in everything. So it'll make solutions with everything. Here we come over here, potassium is as far as we really need to look because that's group 1. If you're not convinced, you could also look at nitrate, which should still convince you that they are both going to be aqueous. Now, what about this last guy here? I is iodides, which is soluble in everything, but again, there are some exceptions, right? And is this one of the exceptions? It is. It's because it has lead with it, right? So instead of being soluble like it normally is, it will be insoluble, and this would be your yellow solid that you would actually make if you put those two solutions together. So you can actually pour two solutions together, and because they are solution, like I talked about before, basically they're ions floating around, and those two ions, the lead and the iodide, will come find each other and make this yellow solid and actually come out of solution, which is why you could see the solid being formed because it's no longer floating in the solution. And essentially, it kind of came out of the solution when they come together. Any questions on that there? All right. Solubility rules, if you need them, would probably be provided for you, I think. You just need to know how to use them, I think. Yeah. All right. Then let's talk about solutions and solubility as well. We talked about the idea of like dissolves like. So as I mentioned before, pretty much we're going to get some good mixing when we got everybody using really the same type of interaction that they use with themselves. The solubility of a solute does depend on temperature. Typically at a higher temperature, you will have a larger solubility of a solid in a liquid. That is why they tell you sometimes you're trying to dissolve something, just kind of warm it up a little bit. And when you warm it up, you're doing a couple of things. Definitely when you warm it up, you're adding more energy, right? Going to get everybody moving a little bit more, even that solid, right? It's going to pick up a little energy. That's going to incorporate them and allow them to sort of dissolve out and start the dissolving process. At a lower temperature, you have a larger solubility of a gas in a liquid. So at a lower temperature, right, my gas molecule, which is my circle, will it be moving faster or slower at a lower temperature? Slower. So it's just going to kind of take us longer time in that liquid part, right, as it's trying to get out and come out of the container and come back in the container. So it's going to take a lot longer for it to get out of the liquid part because it's not moving as fast, right? The solubility of gases also depends on pressure. The higher the pressure, the larger solubility of gas. In a liquid, for example, that's known as Henry's law, also known as like the soda can example, right? You have a soda can, right? You have a bunch of CO2 molecules, gas molecules, dissolved in the liquid part, right? Before you pop the top of your soda can, right? It's under a lot of pressure. When you pop the top, you release all that pressure. And what do you sometimes see coming out, fizzing out? Yeah, you see that. That's basically the CO2 escaping, right? And you're able to do that because you release the pressure. You also gave it an escape point, which is really bad because when you leave your soda open for a while and you come back to it, it tastes, yeah, because all your carbon dioxide just floated away, right? And it's no more carbonated anymore. Basically, it's just a flat, syrupy water at mess at that point, right? You still drink it because you're thirsty. It happens, right? And you do that thing. But that's the idea there. Again, before we pop the top under a lot more pressure, it's going to keep that carbon dioxide in the liquid part of it and keep it all bubbly, I suppose, right? Now, there are some ways that we can classify solutions. So let's talk about that. There is a limit to how much you can get to dissolve at a given temperature. You can have a situation where you have too much solute dissolved in a solvent. That can be a situation known as a saturated solution. A saturated solution is a solution where at that given temperature, you pretty much hit the point where that's all of it's going to dissolve. No more will dissolve at that point. You've hit the maximum amount of solid that will dissolve at that particular point, sometimes referred to as the saturation point. You pretty much hit the maximum amount of solute that will dissolve in that solvent. If you decide to add more, say sugar, like my Costco example, at some point you're going to hit a saturated solution. And if you keep adding like that sugar, it's not going to dissolve. It's just going to kind of pile up on the bottom, right? The opposite of that is an unsaturated solution. An unsaturated solution, you have not hit that point of saturation yet, which means if you continue to put solid in the water, for example, it will continue to dissolve. And it will continue to dissolve with no problem because it's unsaturated. It will continue to dissolve until it hits what? Until it hits a saturated solution. So you can continue to dissolve your solute in that solvent, and it will continue to dissolve until eventually you will again, if you keep doing it, hit a saturated solution. And at that point, no more will dissolve. Any questions on that there? There's also a supersaturated solution where you have way too much dissolved in that particular solvent. The way you make a supersaturated solution is you actually dissolve stuff while you're heating it up. So as I heat it up, right, the solubility is going to increase because I'm increasing the temperature. So I could dump a bunch of solid in there and it's all going to dissolve. And after you do that, you let it cool down. When I let it cool back down from the higher temperature, what happens to solubility? It goes up or down? It goes down. Problem is, at this point, you've already dissolved it. It's already in the solution or in the solvent. So what you create actually is a quite unstable solution at that point because you essentially have too much solid dissolved, but you already got it dissolved. So it's still a solution at this point. It is so unstable that if you just take a speck of whatever you dissolved in there and drop it in there, it will go, oh no. And all the solid will come out of the solution. And it will go from like a liquid state to a solid state by just dropping like the teeniest little bit in there. It's like enough to like push it over the edge, basically, because it's really unstable. Those type of solutions are also so unstable that if you're not careful enough, and I've done this on many demonstrations, and you just like tap it, it will cause everything to come out of the solution because it's that unstable without you adding anything. So you have a nice solution, you just kind of gently tap it, and you'll just see all the solid come out of the solution because you've increased the solubility by heating it, got a bunch of it to dissolve in there, then you lowered it back down by cooling it back down, and now we got a problem because now we got too much dissolved where it shouldn't be, and it recognizes that at the lower temperature, and that's why it's very, very unstable. It's a cool experiment. They used to do that a lot at schools, but they lost a lot of thermometers because they would always in those experiments tell the kids, put your thermometer in the test tube. And then when it would cool back down and become hard, they had all their test tubes, a thermometer stuck in the test tube like an ice, like a popsicle. So like, how do we get it off? Break it? No. But schools lost a lot of thermometers here in those experiments. All right. Other ways that you could classify solutions is concentrated. A concentrated solution is one that has a lot of solute dissolved in it. One of the most common units of concentration, as we'll talk about in this chapter, is molarity. Molarity is capital M. It stands for moles per liter. You might have seen it on some of your bottles where it says like 18M. I hope not, but that's pretty strong. Maybe it says 6M. So that M stands for molarity as a concentration. The bigger the number, the stronger it is. You should be super careful. Yes, if you see a big number next to an M on a bottle. A dilute solution, which is typically what you use probably in your labs, is a solution that has a smaller amount of solute dissolved in it. Usually we take a concentrated solution and we dilute it down and use it as a dilute solution, right? And common example, right? We grab the big gulp there before you come to class, right? With your ice and drinking it, and it tastes really good. You leave it in your car, you come to class, you come back out, you give it a taste. Maybe it doesn't taste so good anymore, right? Because all the ice has, right, melted and diluted it in water, right? And not as strong as it was because now you have a lot more solvent molecules, water molecules in there. And we, again, still drink it depending on the situation, right? You're like, I don't got anything. The car's 100 degrees. I'm going to go with it. All right. Any questions on that? We're going to talk about electrolytes now and what they are, I think. We'll talk about that. Actually, we'll go here and talk about. Let's talk about electrolytes. Electrolytes are substances that will break apart into ions in water, basically, or solution, basically. And it's the presence of these ions that help it conduct electricity. Now, there's different types of electrolytes. There are strong electrolytes. Strong electrolytes will 100% break apart in solution. And you pretty much have all ions. You have none of the whole units together. So if you had a sodium chloride solution in the actual solution part, when it's actually in that solution, it will break apart into sodium ions and chloride ions. 100% of what you got going on in that solution are those ions. You have none of these guys still together. They have all just completely broken apart in ions. Because it has produced so many ions in solution and it completely breaks apart, it is able to conduct electricity really, really well. It will conduct electricity very well. The classic example is the light bulb example, like you might do in this lab. So if you take a strong electrolyte and you take a light bulb that has some electrodes to it and you stick the electrodes in it, the light bulb will come on very, very brightly. Yeah, because it has no problem conducting electricity. So it'll be very, very bright, the light bulb. Now, if you have a weak electrolyte, it will mainly stay together, but it will break apart a little into ions. So you're still conducting ions, so it's still able to conduct electricity, but nowhere near what a strong electrolyte could do, but because it will mainly stay together. So if you took something like HF, which is a weak acid, and when it's in solution, it will break apart a little bit into these ions. So you will mainly have this whole thing still together, but you will produce a little of these ions. So in that particular solution, you basically have HF floating around, but you do have a little bit of H plus and a little bit of F minus floating around in the beaker. And because it's still there with a little bit of ions floating around in the beaker, it's still able to conduct electricity. So the example with the light bulb, if you do that light bulb example, it will turn on, but it'll look kind of dull or dim, like it's dying, but it's still able to conduct a little bit of electricity in that particular case. Also, a major difference in the way the reactions are written. Strong electrolyte, one-way arrow, yes. Weak electrolyte, two-way arrow, yes. That is a reversible reaction, and that is how you know for sure it's a weak electrolyte. When you have a weak electrolyte, you will have that arrow that heads in both directions. And when you have that arrow that heads in both directions, there is a forward direction, which goes from reactants to products. And there's a reverse direction that goes from products back to reactants. So it goes in both directions, and that is definitely how you can recognize an equation that this is a weak electrolyte when you see that. Lastly, there is a non-electrolyte. And a non-electrolyte will dissolve in water, but no ions are created. And because it does not create any ions, you will not conduct electricity. Sugar, right? Sugar is a covalent compound, as we saw earlier, carbons, hydrogens, oxygens. If you have solid sugar, you could put that into water and it will dissolve into aqueous sugar, but it will not break apart because they are sharing electrons. So it's not going to create any ions. So you will not have any ions in that solution. You would just have a bunch of sugar molecules floating around, no positive guys, no negative guys. So it will not be able to conduct electricity. Again, if you put the light bulb in that, not going to go off. Yeah, so it will not go off in that type of situation. So a strong electrolyte, how do you recognize it? Well, you have a one-way arrow, you have some type of ionic compound on one side and ions on the other side. Strong. Weak electrolyte, how do you recognize it? Like I said before, you have something on the left-hand side, you have these two arrows, and you have some ions on the other side. And a non-electrolyte, you'll pretty much have the same thing on both sides, except that it will dissolve, but you will again not have any ions, basically. So that's the way you can recognize a non-electrolyte versus a weak electrolyte or a strong electrolyte if you look at the equations. Question on that there. By the way, is pure water a good conductor of electricity? Pure water. Pure water is a terrible conductor of electricity if it's pure water, because water is also covalently bonded, right? So there's no ions, basically. Remember, though, that the water that comes out of your shower and house is not pure water. Yes, there are ions in it, and you will electrocute yourself if you decide to blow dry your hair in the shower, right? That's why we don't do that. I don't know why you don't do those things. Don't do those things. Nice warning on the video as well. So don't do those things. Bad idea. Or listen to the radio in the shower, I suppose, as well, unless it's waterproof, I suppose. But they actually put ions into your water to purify it, right, and clean it. So they actually insert ions into your water that comes out of your pipes. So it actually is a good conductor of electricity. By the way, we talked about sodium chloride. If I had solid sodium chloride and I stuck my little electrodes in there with my light bulb, would it go off? It would not. It would not go off because it needs to be dissolved and release those ions into solution to float around. So it would not in that particular case. Any questions on electrolytes? Yeah. Let's talk a little bit then about equivalents. Now, a lot of body fluids typically contain a mixture of several electrolytes. And an equivalent is the amount of ion that's equal to 1 mole of positive or negative charge. So how do we figure out sort of the equivalence? It's based on the actual charge. So for example, if I have sulfate, charge of sulfate is 2, yes, minus. It's actually the number here is the only important thing. We could actually come up with a conversion factor, like 1 mole of sulfate will give me 2 equivalents. And the 2 comes from the charge. Now, if I had sodium and 1 mole of sodium ions, how many equivalents should I have? Charge is +1, right? So it would be 1 equivalent, yeah? Doesn't matter if it's positive, doesn't matter if it's negative. You could use those as conversion factors. So very commonly, we will use these as conversion factors to convert from really this unit here, which is molarity, which is, again, moles per liter. So for example, if I had a 0.25 molar solution of sodium chloride, and again, this big M means that if I take that M out, it is these 2 units, and the number stays with the moles part, and it's per liter of sodium chloride. That is the same thing, and as we'll talk about when we really get into molarity later on in this chapter, I highly recommend you do that, because when people do not turn the big M into moles per liter, they forget all about the liters part. They have no idea where the liters part is. They don't even remember it's there. They just think moles and moles. That's the only thing I think about. So it's a really good idea to pull that out. We calculate molarity by taking the moles of whatever it is, the solute, divided by the total liters of solution, and that will give you your molarity. Now, if we wanted to know what this would be in, say, equivalents per liter or milli equivalents per liter, which are 2 very common units that are used sometimes for this type of stuff, electrolytes, we could do that because we can figure out our relationship here. First off, the relationship when I look at something like sodium chloride and it breaks apart into sodium ion and chloride ion. if I know the molarity of this guy as 0.25 molar, the relationship, just like stoichiometry here, for every 1 mole of this, how many moles of sodium ions do I get? 1. It's a 1-to-1 relationship, which means if I'm interested in just the molarity of the sodium ions, you would take 1 times 0.25 molar, and it would be 0.25 molar sodium ions. What would chloride be in this case? It is a 1-to-1 relationship, right? And that means that if I was interested in just the chloride ions, I would take 1 times 0.25 molar, and that would give me 0.25 molar for the chloride ions. This is how you can relate molarity into the individual ions. It's basically done by kind of mole to mole relationship. For example, though, if I had, say, calcium chloride here, right? And we have the same 0.25 molar. When this breaks apart, I get a calcium ion, right? And how many chloride ions? 2. Yeah. That affects the concentration. And in this case, it's a 1-to-1 relationship between these two guys, which means I would take 1 times 0.25 molar, and that would get me 0.25 molar calcium ions. But what is the relationship between this guy and the chloride? It is a 1 to, you get twice as much, right? You get a 2-for-1 special on that when it goes for a swim. Get twice the chloride than you do the calcium in this case, right? So you got to multiply the concentration by 2. And that means that the concentration for chloride would be 0.5 molar for chloride. And again, it's twice as concentrated. It's basically what that number means, right? I have 0.25 molarity of calcium floating around. I got twice as much molarity, right, of chloride floating around, because again, it's a 2-for-1 deal on that. You get twice as much chloride go into the pool as you do calcium in this particular case. Any questions on that relationship there? Yeah. What's that? Yeah, so it is, you can leave it one of two ways. You can leave it as molarity, big M, or you can turn that big M into moles per liter. It's perfect fine. And you wouldn't leave it as M over L. You would want to write moles per liter. So how does this help us with like equivalents per liter and stuff like that? Let us do this one first, and then we'll do this one here next. So we'll start with this one. And let's say we did have this sodium chloride, which we now know has 0.25, and I'm going to turn it into those units, moles per liter of sodium ions. And again, that moles per liter is the same thing as the big M. And it also has 0.25 moles per liter of chloride ions. And now in this case, we want to turn those into equivalents per liter and milli equivalents per liter, right? First off, which unit I don't have to play with in this one? Which unit is good to go? The liters, right? Liters are on the bottom of my original number, and liters are on the bottom of what I want to end up with, right? So I don't even have to do anything with that part, right? The only part that I have to change is the moles on top to equivalents, right? So that is what we're going to use. We saw earlier that if I had 1 mole of sodium ions, that would give me 1 equivalent, right? And again, that is from the charge. So if I take my sodium, 0.25 moles per liter of sodium, and I use this as a conversion factor, I would want moles of sodium on the bottom, ions, and 1 equivalent on top. The moles of sodium will cancel. That will give me 0.25 equivalents per liter of sodium. Yeah. Now, if I want milli equivalents, right? So the way you can remember this is like this. How many milliliters are there in a liter? Yeah, there's 1,000 milliliters in a liter. So how many milli equivalents would there be in an equivalent? 1,000 milli equivalents in 1 equivalent, right? It is the milli conversion. It's the same conversion, right? So we could use that. This would be one of the answers, by the way. We could also use that as a conversion factor, and in one equivalent, there would be 1,000 milliequivalents. Those will cancel, and you'll end up with 0.25 times 1,000. Move that decimal 3 places, probably. Or 3 places, but I hit 1,000 and not 100. And I did it again, but we'll go with 250 milliequivalents per liter of sodium ions. Any questions on that calculation? So it's really equivalent, just a conversion factor to convert a concentration unit from one concentration to another. We could do the exact same thing for chloride. So if we do the exact same thing for the chloride ions that are floating around the solution, for every 1 mole of chloride ions, how many equivalents? 1, right? Based on the charge, -1, 1 is the number we're looking for. And we could do the same type of conversion. We would have 1 mole of chloride ions, 1 equivalent. Moles of chloride will cancel. Will leave us 0.25 equivalents per liter of chloride. And we could also do the same conversion into milliequivalents, 1,000 milliequivalents per equivalent. And that will get me 250 milliequivalents per liter of chloride ion. Yeah. Any question on that calculation? Now let's take a look at the calcium chloride to show you how it's a little bit different in terms of maybe what we end up with to finish it up on here. So we also had, we're going to look at this guy now, our 0.25 of our calcium chloride. So in that case, we had 0.25 moles per liter of calcium ions in that solution. We also had, remember, because it's twice as concentrated, 0.5 moles per liter of chloride ions in that solution. We again want to do the same thing. We want to figure out what those concentrations would be in equivalents per liter or milliequivalents per liter. So we'll start with the calcium. For 1 mole of calcium ions, how many equivalents will I have? It is 2. It's just the number, right? So it would be 2 equivalents. So if we do our first calculation here, 0.25 moles per liter of calcium, 1 mole of calcium ions gives us 2 equivalents. The moles of calcium will cancel. We'll leave us with 0.5 equivalents per liter of calcium, which would be one of our answers. We also could do our milli conversion on this guy like we did on the previous problem. 1,000 milliequivalents in an equivalent will give us 500 milliequivalents per liter of calcium ions. Yeah. Question on that one there. Now, again, we're going to do the same thing for the negative ion in the solution. So we'll go with 0.5 moles per liter of chloride ions. And 1 mole of chloride ions, how many equivalents? 1 equivalent. So again, using that as our conversion factor, 1 equivalent per 1 mole of chloride. Moles of chloride cancel, gives us 0.5 equivalents per liter of chloride. Also, again, doing our milli conversion there with our 1,000 per equivalent. Gives us 500 milliequivalents per liter of chloride ions. So you could calculate the ions that are floating around in an electrolyte solution like an IV bag. And you could calculate the concentration equivalents per liter or milliequivalents per liter. The question I asked here to you ended on, I think, is this question. Is the concentration in equivalents per liter or milliequivalents per liter for each ion in this solution, is it the same or different? The calcium is 0.5 equivalents per liter. The chloride is same. 500 milliequivalents per liter for calcium, 500 for the chloride. Same thing if we look on the previous example. For the sodium, 0.25 equivalents per liter. The chloride, 0.25 equivalents per liter. This is based on the charge, right? And what do we do when we put an ionic compound together that has a positive, negative charge? We make sure it equals 0. It balances each other out. So these concentrations are related to the charge of the ions that are in the solution. And because an ionic compound should have an overall charge of 0, always when you calculate those concentrations in equivalents per liter or milliequivalents per liter for a solution that contains a positive, negative ion, they should always end up the same concentrations, the exact same number when you do equivalents per liter and milliequivalents per liter, because their charges should be balanced out, which is how we put it together in an ionic compound. Any questions on that there? All right.